running. Okay, so here's my benchmarking, DFT versus FFT, and the rates are being printed out in powers of 2, and we're seeing nanoseconds. And FFTs are marginally faster, but as soon as you go slightly large with the DFT, it blows up quick. So now it's 2 seconds versus 344 milliseconds, and things get fast. Well, why? What is this silliness? DFT rate can't be faster than the FFT rate. Did I misunderstand these benchmarks? There's something going on here. Wait. Run rate of the DFT versus the FFT. I think after a fashion it must be held in minutes or something. Shows the rate of the DFT versus the FFT. The rate is the 504 DFT versus FFT, 544 megabytes of RAM. This must be in... See, that's not right. There must be some kind of round-off error going on there, because that doesn't seem right. There's something terribly wrong. This is what it's supposed to look like. There's a time where things cross over. And you guys can benchmark DFT versus FFT. And in fact, if you wanted to, we could make the benchmarking of DFT versus FFT a little project that we do as part of the class. Really. How would we do that? Is there a test in here? Here's a test. Well, the way I would do it is I would create a separate class, maybe something called benchmark. That's probably the thing to do, right? Gesundheit. I think it makes sense to have a benchmark. Shall we do a separate class called benchmark? And what we'll do is we'll do a what shall we do for an input? Ramp data of n. And for n, what do we use? Integer n equals 1 to the shifted over by 4. Isn't that how that works? No. There. So now if I go in through and do that, I should be able to do something like print utils.print, put in D, Alt Enter. What's going on here? It's giving me a hard time. Print utils, import class. I need a parenthesis. Print it out. Print's good. Now take a DFT. Let's see now. What does test DFT do for me? I'll just call it and have a looky-loo. We'll inline this. Refactor. Inline. Keep the method. Oh, he doesn't like that. Let's see what's in there. You got his ramp data. Well, you have to say new DFT of n. Then you call DFT of the input signal. Let's see if that works. New DFT of n, f.dft of the input signal, and I guess that outputs some kind of data. Double PSD equals, oh, that's an array, right? Equals, and if we want to, we can print out the PSD as well. Print utils.print of PSD, and that ought to give us our DFT. Fair enough. Now, how shall we time it? How about in milliseconds? So we'll get start time, then stop time, and then we'll compute the difference, and we'll print out the elapsed time. Does that sound reasonable? So long start time equals system dot get time get millis. I forgot how to do it. I thought it was system dot get time millis. I may have forgotten how to do this. Time utils, runtime utils, dot I don't think that's right. There's a way to get the time. Current time millis. Thank you. So then we do our DFT. Then we do long stop time. And that's equal to system current time millis. And now I really don't need to print answers or anything. Why don't we just print how much time it took? Elapsed time in milliseconds is equal to stop time minus start time, lowercase, start time, and plus quote in milliseconds. And somehow I think he's unhappy because I didn't put in parentheses, because you know those plus signs are overloaded operators. So let's try and see if that works. Voila! Elapsed time 0 milliseconds. Very fast. Let's crank it up, kick it up a notch. Let's do 10. So now it took 128 milliseconds. Now let's do 11. So now what we need is kind of a for loop that's going to run n. So let's do something like that. For integer I equals 0, well, I is less than let's pick a number like 15, I++, and probably what we're going to want to do here is put the whole thing in parentheses and reformat. Oh, you need curly braces for that. There you go. So now I got n. That should be I right here, the number of shifts. and we should start this at some kind of reasonable number. So let's try I equal 4, and that's supposed to be an I over in here. So that'll shift 1 to the left I points. So it'll be 2 to the I. N will be 2 to the I. We'll do the computation, print out the elapsed time, but I think we better also print out N. So quote N equals N quote plus N, I guess it's capital, plus quote space. Somebody's unhappy. Too many curly braces. So now what? We could probably start with I equal to, if this is 4, that's 5, that's 6. I guess we ought to start with I equals 6. What do you think of my benchmarking technique? Good, right? Not bad. So now I got to do the same thing. With a difference, and the difference is I got to do the FFT. Now I can do the FFT right in the kernel of the for loop, so I can alternate DFT versus FFT. So what we'll do is extract a method, and we'll call this test DFT, and then we'll alternate that with a test of the FFT. That way we can reuse the value for N and the value for D. Right? So the input data and N will keep changing, but each time we call test FFT or test DFT, it'll go through and allocate stuff, take a snapshot of the time, and do the elapsed time printout. Probably there's something unsatisfying about that, because I want the DFTs to be all at once, and then I think I want the FFTs to be all at once, but maybe I don't. Maybe I can alternate them. Does it matter? It kind of does. Alright, so if that's the case, we'll do the DFTs all at once, copy, and then we'll do the FFTs all at once. And so now I need a test FFT. I mean, either way, you're going to have to write test FFT. And so test FFT looks just like test DFT, only with a difference. And the difference is there. And then I guess you put FFT in here. Oh, I guess it has to say 1D complex. And then what do you need to do to make this work? Compute forward FFT. Now he looks like he wants float data. Shoot. Maybe I shouldn't be using complex. There's got to be another FFT that doesn't use complex. Here's one that uses double. That sounds handy. FFT1D double. Now what's it need? Compute forward FFT. He looks like he needs a complex part. So I'll just make a complex part in here. Let's see now. Double imaginary array equals new double of d dot length. Then I'll give it the imaginary part. What's he moaning about now? Double double compute forward FFT. D is a double, IM is a double. Oh, what's the return on this? Void. Oh, that's his problem. Yes. You have to call get PSD on that one. It doesn't just return the PSD. That's okay. So then let's see. I excluded all the setup stuff and all the allocation. And the reason you do that is because if you're using this in production, that'll all be allocated once for a given size, and you won't have to keep reallocating arrays. So there's no point in allocating, in measuring how much time it takes to get memory off the heap. I think. So, what could possibly go wrong? Oh, saved by the bell. It's probably telemarketers anyway. They keep calling. I tell them not to, but they don't listen to me. So this is all very educational. Maybe we shouldn't have done so much. Oh, and then it ran again. So check it out. It went from 32 seconds to 4 milliseconds. How's that for execution time? Fast, right? So the tyranny of the squared algorithm. At what point didn't it matter? Well, if the number of samples was 64, it kind of didn't seem to make much difference. At 128, it started to matter. At 256, it was like 10 times slower. At 1024, it was, I don't know. Look at this thing. This thing says 3 milliseconds for 2048. This says 482. Big deal, right? And this is a relatively modern computer I'm using. It's a Intel Core vPro Inside. I don't know what the heck that means, and I'm a computer engineer. If I don't know what it means, how's anybody supposed to know? What is this thing? 2.67 dual core. It's not a barn burner, but it's not a slouch either, right? Coupler 3 gigahertz, an i7. So the key here is the algorithm makes it fast. It's got nothing to do with the CPU. And when you start to think about this number of samples getting large, I mean, really big, like 16K is not that big. Imagine if it gets really big. Then you're spending way more time than it takes to do the sampling. Because think about it another way. At let's assume you have 8 kilohertz, right, sampling with U-law data, and this thing is coming in with an N of 16,000 samples. That's roughly 8 seconds worth of data, right? No, it's 2 seconds worth of data. That's 2 seconds worth of data. It takes him 32 seconds to process 2 seconds worth of data. So that's not even close to real time. And that's not particularly fast sampling. As a matter of fact, 8 kilohertz sampling is particularly slow sampling, because what Nyquist tells us is your maximum frequency is now 4 kilohertz. And so with a 4 kilohertz maximum frequency, I claim that's no better than voice grade audio. Right? If you got audio that goes only to 4 kilohertz and that's it, that's voice grade, almost by definition. So with voice grade audio, which is slow audio, this thing is 16 times slower than real time. Too slow. But if you look at the FFT, it's keeping up. It's doing 2 seconds worth of audio in only 4 milliseconds. Nice. So from the standpoint of being able to do stuff in real time, an FFT is a big win. So we talked about the DFT, we talked about the FFT. I think we beat a dead horse on this. No one should ever use the DFT unless you really don't care about speed, or you have a very short sample. And this is what, you know, the power spectral density of the input signal looks like if you don't do centering. And let's see if I've done a nice centering. Yep, there it is again. The DC component is off to the right. Low frequencies are in the left and right. High frequencies are in the center. That's without the centering. Here's a way you can build a noise filter where noise is being added directly to samples. You do the FFT. You can do a simple thresholding. Say, well, if anything is higher than a certain level, you'll let it through. Anything lower, you'll just zero it out, and that's called a squelch filter in the frequency domain. So here's a nice sine wave. Here it is with noise. Here it is with a whole bunch of partials nicely distributed across the spectra, which I will zero out. And here's the original sine wave back again. So what you can do with those partials that have relatively low magnitude is you can identify them easily in the frequency domain. And then you can squelch them. You can set it into zero. Another nice application for the FFT is the frequency shifting. And I think we saw that, right? That's when you take the frequency and you push it, remap the buckets. Let me see if I can recreate that. It was under sound. Spectrogram. Main. do, re, mi, fa, sol, la, ti, do. Stop. Play. Hit done. And now I think maybe we can do a pitch shift, and we'll use Bob's algorithm, whatever that might be. I have a feeling I have to do a spectrogram first. Let's play it. Can you hear it? It's not loud enough. That's as loud as this thing gets. Let me see if there's if there are external speakers available to me here. As a matter of fact, there are. Maybe this is loud enough. Were you able to hear it? Somewhat? I got it cranked too. Let's see if we can I'll record it something I'll record something first, and then we'll try it again. Testing, 1, 2, 3.
Testing, 1, 2, 3.
Now that's nice and loud. So now we'll do a pitch shift. First, let's look at the power spectral density, the Hanning, and then we'll do the pitch shift. So there's definitely some kind of modulation going on. It sounds like ring modulation to me. Let's see if we can do that again.
Testing, 1, 2, 3, yeah.
So it's padded out at the end. Let's see if we can quit out of this. Let's see, what do we got here? Anything else we need to look at? Centering. Here's where the centering is discussed. And what this will buy me is the DC component at the center of the power spectral density. And what I do is I call centering specifically when I do the inverse transform or the forward transform, because I like to see centered waveforms. Let's see if we can go to the next paper. Okay, so now we're going to get into spectral leakage, which is kind of what I wanted to describe for you when Brian first discussed it, but kind of didn't. Alright, so when you do a basic Fourier transform, what you're doing is you're quantizing everything in frequency space, and that means that the number of buckets plus your sample rate will give you the quanta frequency that you get for each bin. So if you can improve your sample rate, you can improve your precision in frequency, or if you can improve the amount of time over which you do your samples, you can improve your precision in frequency. So I can be very precise in measuring frequency if I can take an event over a long period of time. Or I can improve the sample rate. In fact, the two are the same. And you can see there's a linear relationship between the frequency of the sampling and the delta of the frequency. And that comes right in here. That delta t is 1 over the frequency of the sampling. And you can see that over in here. So when you think about an FFT and you look at the energy in each one of the buckets, what you're really looking at is the energy of a bandpass filter whose frequency is just above and just below the frequency of the bucket. So every bucket number, k, has a specific frequency, f sub k, and you can compute that directly from the sample rate and the total number of buckets in your sample. So having said that, if I told you I wanted to identify an event which was only 2048 samples long, and I had this idea that I was going to sample at 8,000 samples per second, then I would be looking at an event that takes 2/8 or 1/4 of a second. Well, a 1/4 of a second event may not sound like much to you, but in the world of music it could be quite long. That's not playing notes particularly quickly on the guitar, 4 notes per second. In fact, you can do way more than that. So that might not be a good window into the set of events. Let's see now. So for any given number of samples, if I know the sample rate, I should be able to compute the frequency for the sample number. Conversely, if I have the frequency of the input signal, I should be able to get back to the sample number. So it goes both ways. And in fact, if you told me that you wanted to sample something and you had 2048 samples and you were going at 8,000 samples per second, and you were looking to isolate a frequency event that happened at 400 Hertz, I could tell you better look at bucket number 102, because that corresponds to a frequency of 400 Hertz. But wait a minute. If the bucket isn't exactly 102, like in this case, it's 102.4, what do I measure? And the answer is, well, maybe you measure bucket 102, maybe you also measure bucket 103, and this goes to the question of spectral leakage. How many buckets to the left and right of bucket 102 should I measure in order to be able to isolate the energy at 400 Hertz? That's key. And that's going to be a function of what I will call the window. The windowing is going to allow you to focus energy into specific buckets. So if I look at, let's say bucket number 100, I'm really looking at a frequency of 390 Hertz. Well, that's like 10 Hertz off, right? So 2 buckets, right? 5 Hertz per bucket. That's a lot, especially if you're thinking about looking at notes that might be sharp or flat and you want to detect whether or not they're sharp or flat. This is not going to make a very good tuner if you're only accurate to within 10 Hertz. Your ear is more accurate than that, especially when there's relative frequency discrimination. So when along comes the windowing function, and this amplitude modulates the input signal. I'll skip the Greek. And here's a little cosine function, and it makes for a nice smooth amplitude modulation function. That's a piece of a cosine. You can make these little hand windows. You can make a little Bartlett window. There's the Bartlett window, triangular window. This is the vanity window. And so here's my little vanity window with a quintic polynomial being input into a symbolic manipulation program called Maple. And the symbolic manipulation program allows you to read a library for C, and then it can output a way to do the computation in C so that it's optimized for time. Creates auxiliary variables. And so here's a way to use a quintic for arbitrary start and stop values, and then you can input a dilation parameter which ranges from 0 to 1. That's what I call U, and that'll give me a window that'll go up and then down. I call it the lion window, because what else should I call it? And I show you different ways to create the window in advance so that you can use it to piecewise multiply the input signal. And here comes the lion window, and you can compare it side by side with the Hanning window. And one thing about the lion window is it has a longer flat top, and its tails have a taper toward the end. They have 0 for the second and first derivatives. You can't say the same thing about the Hanning window. So the lion window has a flat head, Flash im Kopf, as they say in German. Flash im Kopf. This here is a high-pass filter. Let's see, that's a bandpass filter, pass-band filter. Bandpass and passband are the same. I think I give you a couple of filters. This one, that could actually be an EKG signal. And then we can put it through a passband filter that only lets certain frequencies through. And here's what happens when you amplitude modulate an input signal with a Hanning filter. That's a Bartlett filter. And there's the lion window with the nice smooth edges and the flat top. Flatschimkopf, such as it is. So we could probably run a few examples, see if we have time. I think so. So let's try and do an example with the Hanning filter. What we'll do is let's run our little U-law test. Too loud. Wait, stop that. That's a there we go. That's a chirp. We could speed up the chirp, or we could change the total number of samples in the chirp. Let's give it 2 seconds worth of chirp. Now let's increase the frequency of the chirp. I think that ought to do something. What? I'm not sure. Maybe we ought to increase the frequency just a wee bit more. How about this? That ought to do something. I'm thinking. I'm just messing around. Okay, enough of that. How about there? That's better. So that's kind of annoying. Isn't it? Really? Really annoying. Now what we'll do is we'll get a window and we'll apodize the function. That apodization is Greek for meaning without feet. So we won't have start and stop parts that are very loud. It'll start and stop slowly. So first thing we want to do is get a windowing function. Pick a window. mat1 dot get. Are my windowing functions not in? I forgot where I put them. Let me do a quick search. Find in path. Hanning. Where is it at? Oh, hi. So it's under make Hanning mat1. Okay, that's what I thought. So let's do the following. mat1 dot make Hanning. Now I think I can put an int d dot length. And what's this by me? Double precision numbers. So here's my window. And then what we'll do is we'll take the input signal mat1 dot window. This needs the input data D and then the window. And does that output anything? No. So it alters its input data. So that should look like something a little bit different than what we started with. So now what it's done is it's faded it in and then faded it out. And you should be able to see that here. So now you can see the fade in and fade out. That's clear, right? So it's got a very slow attack, and then I don't know. We can make a different one. Let's try make lion. So now we should be able to decrease the volume, and now you've got the lion with the flat top. Watch him cough. And we should be able to do the Bartlett. Oops. Make Bartlett. It's got the same interface, so you really don't have to do much to change from one window to the next. And that should be more triangular in its shape. And certainly it is. So that's all good. Now that we've done that, we should be able to do a Fourier transform and get the power spectral density of our chirp and then display it. How shall we do that? Better not use a DFT, huh? Better use an FFT. So after this is done, we'll do a FFT 1D double F. Did I do something wrong? Alt enter? Nope. Equals new FFT 1D double. And now I can say something like this. I'll need some imaginary data, so I'll say double imaginary array equals new imaginary d dot length. Isn't that how that works? Oh no, I have to put in double. Yeah, sometimes I forgot how to program Java. And then it happens, and then you have to do f dot compute forward Fourier transform. You give it the real part, you give it the imaginary part, and then this gives you nothing but void on the output. But I should be able to get the power spectral density. Here's the log of the power spectral density. That sounds like a good time, assuming you have a broad notion of what a good time is. And what we can do is we can show it on the O-scope panel. So we'll just paste that on in there. And now I think maybe you're ready for this. Crossing fingers. Now I got an error. Not an integral power of 2. Yeah. So you got to remember, radix 2 algorithm requires the integral power of 2, especially because you're doing that bit reversal thing, the decimation in time, where you're taking the odd parts and the even parts, recursively subdividing the list. So if you don't have an integral power of 2, you're screwed. First thing you do when you go and you look at this, you say, hey, wait a minute, that's not an integral power of 2, but you can fix that, right? You do something like this. 1, shift, and then make up a number. Let's see now. 2 to the 16 is 65,536. 2 to the 32, sorry, 2 to the 15 is 32,000. So 2 to the 14 should be 16,536 or something? I don't know. What is 2 to the 14? You tell me. Let's see. 2 to the 10 is 1,024. 2 to the 11 is 2,048. 2 to the 12 is 4,096. 2 to the 13 is 8,192. So 2 to the 14 is 16,536. No? What is it? 16,300. I was close. Okay. So what is this by me? Oh, it's all the way up in the ceiling here. Yeah, O-scopes aren't really meant to oh, it's pretty cool looking actually. What is this? Well, that's what it looks like. For whatever that's worth. You could probably take the power spectral density of it and see it as a function of time instead of the whole thing all at once. It's kind of neat. You can see all these harmonics. I've never actually visualized a chirp like this before. Maybe we should do a shorter one, huh? So, just sort of do that and see what happens. Wow. It's kind of neat. The frequency domain, it really doesn't look at all like what you'd expect. But maybe in a sense it makes sense, because what's happening is the frequency goes up and then the frequency comes down, and then the frequency goes up and then the frequency goes down. So as far in the frequency domain, that's exactly what you would expect from a chirp, because it's going whoop 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 like that. It's kind of neat. I never really thought about what a chirp looks like in the frequency domain. It's kind of it's very symmetric, interesting function. How fun. Oh, and we use the hand window on that too. So I suppose you would get different results if you use different windows. And that's exactly what you'd expect. Let's see what else. Here's the stuff about the power spectral density, which we have already seen. What I liked about what we had just done is the signal was completely synthetic. How'd you guys make out with the ECG signal? Another synthetic signal, but one that tried to model a real heart. In this paper, what I did was I tried to measure different frequencies of different notes for the purpose of note identification. And that might be very handy for somebody who wants to take a performance and create what's known as a lead sheet. The lead sheet, I don't know if you're familiar with standard Western notation, consists of notes that are drawn on a staff. And each note is supposed to correspond to a different frequency. So if what you can do is analyze input signals that are musical and then assign notes to them, you can create a standard Western music notational lead sheet for it. But when you look at the different frequencies as they come in, one of the things I think is characteristic of them is that they have different harmonic content. Right? It's not all in one. You don't have pure tones. Western music has three basic names for the sounds that you hear from instruments. There's pitch, there's amplitude, and then there's everything else. And they group that into this the term timbre. But timbre refers to the harmonic content of the instrument. And timbre isn't normally something you have a whole lot of control over, because it's what makes a piano sound like a piano, or a guitar sound like a guitar. So unless you run it through a sound effects modification, timbre is something that is characteristic of the instrument itself. How am I doing on time? Good. So now if you've got these different sorts of signals, you can see where the white is, and here down, that's your focused energy. But in fact, there's a lot of energy elsewhere in these harmonics, and the harmonics are distributed all across the spectrum. So you're probably better off identifying the sound not so much by the partial that has the highest energy, but by its signature. So then the question is, how do you create something that's going to identify a wide variety of different patterns, given, I'll call it, a pattern dictionary? Let's assume the patterns have already been sampled and you have note names assigned in what's known in the pattern recognition world as ground truth. Ground truth says if you see this signature, then that equals an A note. If you see that signature, it equals a B note. So then when you go and you do your sampling and you convert it into the frequency domain, how do you compare two signatures to see if which one is more like what you're looking for than some other one? How do you know? Any ideas? How do I know, for example, the first one is an A and the second one is a B? They're both very close to one another. They both have the same harmonic distributions. The difference in the buckets is relatively small. What characteristics should I be using? Well, okay, I'm using frequency. That's fine. But in the frequency domain even, it's not particularly clear. Well, you could choose the largest bucket, or maybe even the largest few buckets. But I like to think that if you're going to use a generalized signature, that the overall magnitude isn't so important. What's really important is the relative distribution of the different partials, because a louder note doesn't necessarily make it more like some sort of given dictionary note than some other note. So what I like to do is a correlation. And you can do the correlation relatively quickly. They call it a fast correlation if you do the correlation in the frequency domain. So there are fast correlation algorithms. And that is probably the topic of the next paper, I hope. Yep, there it is. So now we've got another application, right? What can you do with a fast Fourier transform, or Fourier transform in general? Once you're in the frequency domain, the convolution theorem says I can do fast convolution. I can do frequency shifting. I can do what else? Anything else? You're in the frequency domain, you can do filtering in the frequency domain, right? You say, well, if I want this frequency to that frequency, I can just build a little box and say anything outside of it goes to 0. Right? In the frequency domain, building a filter is trivial. I can build all kinds of interesting and wonderful filters. I can say, well, if noise is always is suppressed below signal, then anything with frequencies below a certain level, I'll just squelch down to 0. So I can build a noise filter. All kinds of interesting and wonderful filters for me. High-pass filters, low-pass filters, band-pass filters, noise filters, you name it. So if you've got a signal coming in from a real sensor, and almost everyone does, then it's going to have noise. It's gotta. And so then the question is, what will you do to handle that noise? Well, if you take the Fourier transform, you can squelch it out. So then comes this next thing. What if you're looking for specific signatures coming in? Well, if you can do pattern recognition with it, and you can identify something that's known and compare it against something that's unknown, well, then cross-correlation is a good algorithm. It's the moral equivalent of template recognition. And if you're going to do the, I'll call it short-time Fourier transform, then you're going to have a sequence of input signals, each of which have a fast Fourier transform signature that you can then compare against your code book, your dictionary. And when you do that comparison, you should be able to determine what code it is that you're looking at. And so that's key. But it's slow. That is, unless you use a Fourier transform. This is the general expression for a normalized cross-correlation. X bar and Y bar, they are the averages for the input signal, which can be easily computed. It's not unlike what we were doing before with the Hurst computation, only with a difference. And the difference is you have a window that travels across, so you can take your input pattern and you can compare it against a whole bunch of different templates at different points in time. Or if it's an image processing template recognition, you can compare a small subsection of an image against the big image and find out where it is. So if you're trying to locate eyes, you can cut out the eyes and then have them travel across the face until it finds the eyes, and then the eyes become the resonant filter, and it says yes with a peak using the cross correlation. Now, you know, the other thing is correlation is something that's not normally normalized in Microsoft Excel. So if you go to the cross correlation in Excel, it's not doing this denominator here at the bottom. What's that denominator equal to anyways? That should look somewhat familiar. On the left, that's a standard deviation, right? That's the signal minus its average. Square up the differences from the mean. Sum up all the differences. Take the square root. That's a standard deviation. On the right, what you have is a standard deviation of the signal against itself, only delayed somewhat. So that delay in the standard deviation is the thing that's going to give you the normalized coefficient for any given delay, and you've got to keep changing the d in the r sub d. So that's recursive. D keeps changing. So that causes the signal to travel across some template, or the template to travel across the signal. You're time shifting. D represents the time shift, the delay. D is for delay. And the other thing is, this is really just a dot product with that, right? That's just a piecewise multiplication of the two signals, and then you're summing it. And that piecewise dot product is interesting only because as D changes, you're shifting the signal when you do the piecewise dot product. Everybody know what a dot product is? You take two numbers, two vectors, multiply them together and add up the result. That's your dot product. You can find that here in the Mat 1 class under the math. I don't know, something like let's see if I can find it real quick. Here, dot product between two doubles results in a scalar. They have to be of the same length. So two vectors A times B, you do a piecewise multiplication of A and B and add up the result, and that's a dot product. Real simple, right? But a sliding dot product says you're going to get a series of results, one for each delay input that you put in for B. So what happens up at the top is a sliding dot product where the delay keeps changing. And then you're dividing through by the standard deviation for the input signal versus the template. And that's what causes the normalization. Here's another way to represent dot product. And the pentagon notation down here between x, pentagon, y, that's a convolution with delay. And the star down and over in here, that stands for the complex conjugate. You guys know what a complex conjugate is? If z is equal to x plus iy, the complex conjugate of z is equal to x minus iy. It's just the negative of the imaginary part. You can do that with a vector of complex numbers, form the complex conjugate. It's the negation of the imaginary part. So let's see now. The pentagon notation is being used here for cross correlation, and so now we're seeing the complex conjugate of x with a dot product against y in a delayed form. In comparison, the convolution is equal to the dot product of x with y reflected about the delay. What's the difference? Well, I'm not seeing a complex conjugate here, although here the comparisons are real valued. It's really just a difference in how things are slid. And I have an example in Excel. So here's the X signal, here's the Y signal, here's Y, and you can see 3202. If you look here, Y1, that's with 3 all the way down at the bottom. Y2, it becomes 32. Y3 is 320. y4 it's 3202, y5 it's 202, so we're shifting it up by 1, y6 it's 02, y7 it's 2. Right? So when you look at y and then you see y1 through 7, you're seeing y, only it's shifted. Got the shifting thing? And when you shift, you do a piecewise multiply. Remember the dot product? Just take the individual numbers, 1 times 0, plus 2 times 0, plus 3 times 0, plus 4 times 3, and then the answer is 12. So the dot multiply means multiply piece by piece, adding up the sum. And so here you see 3 times 3 plus 4 times 2, and you should get 17. And so that's been done in Excel just so that you can see y for each one of its shifted elements, and then the piecewise dot product. And that's what you got to do in the program in order to affect a sliding window dot product. Without dividing, this one's not dividing by standard deviations. But that's just a constant you can pre-compute. It doesn't matter how you shifted x or y in here, you can still do a pre-computed dot product on, you can still do a pre-computed standard deviation. So that's non-normalized sliding window dot product. And so you got, just like the discrete Fourier transform, you got a fast Fourier transform. With a cross correlation, you can have a slow cross correlation and a fast cross correlation. And this is my little fast cross correlation. And the inputs are here. You can print them beforehand and then afterwards. And here I'm doing a shift. And I gotta figure that's all part of the MAT1. So if I go back in here and search for shift, and there it is. There's my shifting algorithm. Shifts by S, numbers D to give you a new number, a new array with the shifted version. I could probably do a shift test. That seems very shifty, right? I'm going to do a shift test and see it work. So we'll start off with some double data. 1, 2, 3, 4, 5. And then what we'll do is shift. Oh, there's already a test shift, isn't there? I didn't even notice. Let's do test shift. There should always be a testing function somewheres. I'll just see if it works. So here it is shifting over to the left, shifting, 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 and then it's shifting off to the end, and then finally it shifts all the way off to the left. So that's my little shifting function. And it looks like it's doing a print every time it does a shift. That's kind of what you'd expect it to do, I think. It's padding in zeros as it shifts things off to the left, so it doesn't really care how far you shift. Shifting dot product. So a shifting dot product is really a correlation, a non-normalized correlation. So here's my input signal. Here it is prior to being shifted. Here it is after shifting. And now you can see 0 times that, 0 times that, 0 times that. Now 3 times 4 is 12. Now I shift out again, and I got 3 times 3 plus 2 times 4, and I should get an answer like 17. So that's 8 plus 9. Sort of feels right. And so similarly, the shifting dot product can be computed until you're done. Though there's all zeros in there, I suppose. So now, just like we got a convolution theorem, there's a correlation theorem. And the correlation theorem says that you can do a fast correlation with a Fourier transform if you take the complex conjugate of the Fourier transform and then do the multiplication in the frequency domain. And that says, let me see if I can say this right. Correlation in the time domain is equal to multiplication by the complex conjugate in the frequency domain. So if you can form a complex conjugate in the frequency domain quickly, and you can, because all you have to do is multiply the imaginary part by -1, then it's just a multiply and you get the correlation happening. Pretty cool, right? But check it out. You don't just want to correlate with one thing, right? You want to correlate with a whole bunch of things in your code book because you're looking for something, right? So if you told me, well, there's 8 notes and they're all major, I'd say, great, we'll have to get all 8 notes and we'll have to put them into our code book. And we're going to have to take a Fourier transform. But wait, I don't have to do the Fourier transform as the signal comes in. I can do the whole Fourier transform for all the sample notes that you're wanting to compare against in advance. So if the input signal is G, and that's what you're going to do the Fourier transform on, then the code book can be the complex conjugate of the Fourier transform of all the different possible test signals that you know about. And so they can all be stored in your code book in the frequency domain. And then it's a simple multiply in the frequency domain. And if all you want to do is maximize the energy that you're looking for, you don't even need to do an inverse Fourier transform. All you have to do is find out what the total energy is after you do the multiplication. And blammo, you've got a relative answer. So that's a big win. You only have to do the Fourier transform once on the input signal for each window in time. So if you're going to do the spectrogram, you're still going to have to decide how long the longest event will be at a given sample rate. So the sample rate may be a given, but the event time may not be. Right? I mean, that may be something you have to measure, or maybe it's something you have no control over. So that's an application-oriented question. And so I've got 2 kinds of correlation available for you to play with: MAT1 slow correlation and signal processing CORAL, which is the fast cross correlation. And they both give you the same answers. So then I wrote some test code to benchmark the fast correlation against the slow correlation, just the way we did benchmarking of DFTs versus FFTs earlier today. And well, it's orders of magnitude faster. Kind of depends on how big the window is. So this goes to the big question of sample rate and event time. If your sample rates are relatively high and your event times are relatively long, you may end up with much larger window sizes. With a window size of 1024, you're kind of looking at 8,000 samples per second for our voice grade audio system, so that's 1/8 of a second, which might strike you as being particularly long, depending on your application. So then comes the big question, what can you do with it? Aside from the obvious musical applications. Any ideas? You're not allowed to sit like lumps on bumps. It's not permitted. I guess we're out of time here. Okay, how's this? For a homework assignment, and I'll email this to the group with a, I guess I should use Blackboard for this, right? What's a convenient way to why is this starting me like this? Please wait while the modules load. That's some bizarre thing going on here with Blackboard. Does anybody know what's going on here? Content. Assignment. Alright, so what number would this be now? Homework 5? Maybe? Write a small algorithm to identify a, let's say, biological pattern. Let's see. Write a small, I'll say, English language, passive, let's see, paragraph. Write a paragraph. Write a paragraph to identify a biological pattern of interest using fast cross correlation. Okay? Assume the pattern is well understood. How will you identify the different patterns? What will you use to, let's say, get the patterns into your computer system? So, for example, suppose you wanted to identify faces. You might digitize a bunch of faces, use those as your base comparison. You might have a name associated with each face, and then when somebody takes a picture of the face, it should be able to say, oh, that looks like so-and-so. Oh, that looks like somebody else. So that's a kind of pattern recognition. When you're taking in signal data and converting it into symbolic data, that's pattern recognition. So now suppose somebody said, well, I want to identify REM sleep to see when people are in rapid eye movement deep sleep. So you might need a technician to look at the EEG normally, but here in our fast cross-correlation system, maybe we could use our system to find out what level of REM sleep you're on. Or suppose somebody said, oh, I'm having, a heart attack or something, right? Well, there are probably certain things that give that away, beats that are irregular, and we can Google them and see what a heart attack looks like. And those are the kinds of things we can input into our system. So there's all different kinds of examples in the body that allow us to identify certain things that we might like to characterize. And so what I'm asking you is to think about those different things and write a paragraph or two, if you will, as part of your homework. This is not a programming assignment, but it's thinking about how an algorithm might be formulated to try and identify certain kinds of patterns in an input signal. So that means that you're going to have to Google around. One thing I used to do, I used to work in the chronobiology lab at Cornell. We had people who were subjected to the deprivation of light. They were locked in rooms and they were free wheeling with their circadian rhythms, their sleep-wake cycles. And whenever they were about to take a shower, temperatures, body temperatures would shoot up, and we were measuring those with our little mini computers. So there are these things that you could identify rapidly when all kinds of interesting signals that you wouldn't expect. And so there are things that we can now measure conveniently with our sensors. Presumably you can put the sensors anywhere you like, but I've seen people selling these sensors in Best Buy so that they hook to your iPhone, and there are apps for everything. They're sports sensors. They put sensors in your shoes. They got these things. They transmit back your weight, so you can be like really anorexic, continuously feeding back on how much you've eaten. There's pulse oximeters. They measure your actual heart rate or your blood pressure. I mean, they've got everything in your shoe except for a rotary dial phone, so you can call control, which is important if you're Agent 86. So I'm thinking that there's there are compelling arguments for putting sensors with iPad apps into all of these things. It's the next generation of gadget. And I wonder, what can we do with our computers to figure out what's going on with all of this interesting and wonderful data? So I'm going to ask you guys to come up with creative and wonderful ideas, and they don't have to be practical. That's very key. So just let your creative juices flow. And let's see what you can do with your newfound toolbox filled with normalized cross-correlation algorithms. Like I said, because you're probably going to think of stuff I haven't thought of yet, and that's really very good. So let me send that out somehow. There's like no submit button. Shouldn't there be like a submit button? Add rubric, allow single attempts, limit availability. I guess we're going to have to say track number of views. I don't want that. Submissions are due but are marked late. So this is really annoying what's going on here. How does one scroll to the right? Oh, okay. There we go. So that's when it's due at 2. After that it's marked late. Recipients, all students. Click submit to submit. A value must be provided. Really? This is pissing me off. Okay, 100. Okay. It's a Blackboard thing. I just have to learn it, that's all. Submit. Alright, we've got a success. This is great. So now you've got a nice little homework assignment, and it's really just about thinking about the kinds of things you might be able to recognize. Let's think about some of the biological signals that might be interesting for us. The Thanksgiving detector, for example. It knows when you're pigging out, and then the pig out thing, it starts to tweet onto Facebook or whatever. Do you tweet onto Facebook? No, that's twittering. Oh, all right. Well, whatever it does with Facebook. I honestly, I don't think you can teach a dinosaur like me to tweet. So stop me before I mix another metaphor. Tonight there's going to be an IACT meeting, and you're all invited. I don't know if you've had an opportunity to see, but if you go to inventus.org, it'll be in the Dolan School of Business within the dining hall starting at 7. And Manny Ratafi will talk about medical devices and how you can bring these things to market, commercializing a product. So if you've got this idea for the next great medical device, rotary dial phone in the shoe, there's probably better ideas. Actually, that's not even my idea. So I think Mel Brooks says that Buck Henry thought of that one. Anyways,